So, but just a preview. It's pretty simple. You're just going to use an equation. So c equals the speed of light. This symbol is called nu. Nu is the frequency. And we have lambda. Lambda equals the wavelength. And we kind of touched on this a little bit when we were talking about proportionality. So when one is directly proportional versus something that is indirectly proportional. Okay, so the speed of light, which is a constant, which is always going to be 3.00 times 10 to the 8th meters per second, is going to equal lambda times nu. Come on. Okay, so in this case, frequency is measured in the units of hertz. Hertz is equivalent to 1/seconds. So 1/seconds will equal 1 hertz. Okay, so if we look at our equation here, we want to solve for, they want to know calculate the wavelength, right? So we want to solve the equation for the wavelength. So we want to solve for lambda. So we get lambda equals c over nu. So as I said, c equals 3.00 times 10 to the 8th meters per second. And nu equals 7.50 times 10 to the 14th. Hertz. So if we plug that into the calculator, of course, calculator. Okay, so I'll get 4.00 times 10 to the minus 7 meters, but they want it in nanometers. So how do I change it from meters to nanometers?
I have a question because when I put it into my calculator, I think I did something wrong.
Okay, so the way that you want to enter it, let me see if I can pull up a calculator. 1 second. Can you guys see that? See my calculator? Put this trying to find a spot for it right there. Can you guys see it now? The calculator? This is not like mine. Let's see. It still should work. So when we enter our numbers, you want to enter, you'll see either EXP or EE. They both mean the same thing. What type of calculator do you have?
A TI-84.
Okay, let me see if I can find a TI-84 case. Okay, so it looks like this, right?
Yeah.
Okay, so what you want to do is, you see that the EE in blue right here? I'll put it towards the top.
Yeah, I see it.
Okay. So what you want to do is you want to hit your second button. You want to hit the EE. So when you type in your exponents, you're going to type in 3.00, and then you're going to hit shift your second. Then you're going to select the EE. And then you're going to put in, since these are all positive values, you're just going to type in 8. So that EE represents 10 times to whatever power. Okay. And then if you do it this way, if you do it the other way, you have to put in parentheses, right? If you do it this way, you don't have to put in parentheses. Does that make sense? So like if you use the 10 to the X, right? You're going to have to put in parentheses for that.
Okay.
Okay. So, and then you would put divide, and then you type in this number, which is 7.50. Oops. Second. EE to the 14th power. And then you hit enter and you'll get your answer.
Okay, I got it. Thank you.
No problem. Yeah. And it's funny, that's one of the most common mistakes that a lot of students make on the exam. And so they'll sit there and plug it into the calculator wrong. The other thing is that EE, when we're doing like a negative exponent, let's say this was negative 14. So we'd use this symbol here, the parentheses negative, to show that that's going to be a negative value. You don't want to use the negative value or the subtract button. Does that make sense?
Yeah, it does.
Okay. Okay, so let me clear. Okay, so oops. I guess we should finish the problem too, right? Okay, so then if we go ahead and finish this up. So what is the conversion from millimeters to nanometers? Does anybody remember? We talked about it in chapter 3. Let me give you a hint. What number starts with an N? Brittany, what number starts with an N?
9.
9. So 1 meter is equal to 10 to the 9 nanometers. Okay, so those units are going to cancel out, the meters are going to cancel out. So if we look at our exponents, we have 10 to the minus 7 and 10 to the 9. So what do I do with those exponents now?
Don't we have to like multiply them?
Not multiply them. We'll just add them since these numbers are being multiplied with each other, since both of these are both base 10, meaning they're 10 to the whatever power, we take the exponents and just add them together. So 7 minus 7 plus 9. It's going to be what?
Is it 2?
Yep. So it's 10 to the second power nanometers. Okay. Do you guys see that?
I was looking at the chemical packet right now, and I don't see like the conversion for nanometers.
Yeah, I don't have those on there. I want you guys to remember those because you're going to run into those quite a bit. Nanometers, micrometers. So, like I said, I always remember 10 to the 9th nanometers because 9 in nanometers equal 1 meter. I know 1,000 millimeter equals 1 meter because I know mil in Spanish means 1,000, right? Is that true?
Yes.
Okay. And then I know picometer is 10 to the 12th. I don't know why I remember that one, but I always do. And I know centa means 100 because century. So 100 centimeters equals 1 meter. Yeah, so I don't put those on the exam, but sometimes what I'll do in the question, I will give you the conversion so you don't flounder too much. So it'll be written in the conversion. But I like you guys to try to remember that because you're going to run across that quite a bit. The other one that you're going to see a lot if you go into nursing or in medicine is micro. So you'll see it written as this. This guy's called mu. And so a micrometer is 10 to the 6 meters equals 1 meter. So 10 to the 6 micrometers will equal 1 meter. Another way that you'll see micro written as is MC. You guys will see like MCG. Have you guys ever seen that on a bottle?
Yeah.
Okay, so that's the other abbreviation for micro. And so if I said I have 10 to the 6th MCG, that will be equal to 1 gram. Okay. Does that make sense?
Yeah, it does.
Okay. So, but I like you guys to learn those, you know, and it takes a little bit, you know. When will the exam be? The exam will actually officially open up tomorrow, and it'll be open till next Wednesday, officially. So it'll be due technically next Wednesday. But again, this is really at your own pace. So if you need a little more time, don't worry about it being late. So I can get everything done. Okay.
So if we turned in my things like maybe like a day late, we won't like be like docked points.
That's right.
Okay.
It shouldn't be. I'm still, there are things that I think I know on Canvas and on Chem 101. And then the next thing I know, it's doing crazy stuff. But usually when you let me know, I try to get it fixed at some point. Definitely well before you get to your final grade. So. Okay. So let's see. The other question was 50. I'm having a little struggle here right now. There we go. Okay, clear the screen. Oh yeah. Yeah, we got to delay this one a little bit. Okay, so which of the following electron configurations? So which of the following has the electron configuration 1s, 2s, 2p? So we haven't gone over this yet. We'll be going over that today and probably next week. So I'm going to postpone this homework by a little bit so that we can actually go over it.
Okay, because I was like, yeah, because there's other problems like that and I didn't do them. So like that's why I was kind of just asking for like one of the like one example.
Yeah. Yeah, so I'll have to adjust the time schedule a little bit. So it's okay. I'm ambitious, you know. I want to get you guys through it fast and painless. Let's see, edit. So let's see, we'll make it due next week. So that gives you enough time to learn the material. Okay. Okay. Okay, so then that's going to push us back on your other homeworks. Let me take care of that real quick, and then we'll get started on the chapter so we can actually learn the stuff that you need. Okay. So we're going to be talking about electromagnetic radiation. This is going to kind of help us understand what's going on in the case of the electron. And unfortunately, I have a really cool lab that I like you guys to do, but I usually do it face-to-face, so it's a little bit harder. So we have to make some modifications. And you guys did the simulations. Did you guys do the flame test? Where in the simulation, you stuck the loop into the flame and then you saw colors?
Yeah.
Okay, good. Okay, so that's the experiment. It's so much better in person. Although simulation isn't too bad.
I also wanted to know when will the lab recording be posted? Because I kind of got like lost in one of like some parts of the lab and I just want to be able to like review.
Okay, it wasn't posted yet. Let me find out. I might have not published it. So I'll take a look at that. Let me put that on my list. And so it should be up today.
And also, does our lab need like our lab report need like a hypothesis and like a purpose?
Yep.
Okay, just making sure.
Yeah, it should. Anytime that we do some type of physical lab, you should always include a hypothesis and a purpose. So your hypothesis is your hypothesis. I shouldn't have to give you that. And the purpose is kind of like, you know, what is it really that you're supposed to be getting from the lab, right? So what was it that we were supposed to get from the last lab that we did?
Oh, when is that due? Because I think there's no assignment for that.
Yeah, it's due. Technically, it's due this Friday. But again, everything is done at your own pace. If you want to wait till the last minute to try to turn everything in, more power to you. But try to get it done. I say try to get it done on the times that it's due because it makes it so much easier for you. And then you kind of have an idea of where you're standing in terms of everything. Done everything that you're supposed to do. You've already got it turned in, and you don't have a whole bunch of stuff waiting on your plate. Does that make
Okay.
sense?
Yeah.
Okay, so let's start talking about these electromagnetic radiation. Okay, so energy basically exists in a form of electric and magnetic waves. And so if we think about some of the things that we experience in our own life, right? So for instance, how many of you guys go to the doctor and have had x-rays done?
It's been a while, but yes.
Okay, so you've had x-rays, right? X-rays is an example of electromagnetic radiation, right? So you notice that they put that lead shield over the parts of it that they don't want you to be exposed to. That's because you have these waves that are sitting there that are of energy that are penetrating your body. And because those waves of energy are penetrating your body, what happens is that your bone and everything kind of blocks those waves. They kind of absorb those waves. You have less energy focused in that area, where something that's clear is able to go straight through. Or something that's able to reflect it, it reflects back, right? So you get a contrast image as a result of that. You get imaging as a result of that happening, right? But in that case, you're looking at energy, right? It's energy that's entering your body in that case, right? And that energy can do damage to your cells. And so that's the reason why they put the shield over the parts that they don't want you to get shielded by, but they only put it on the areas that they really want to take a look at. Okay, so we also have UV. You know, you guys worry about you guys get those UV blockers on your sunglasses and stuff, right? UV stands for ultraviolet. We have visible light, you know, white light. So that's visible light. We have infrared light, the magnetic waves, those radio waves. You guys bump to the radio as driving down the road, right? So those are all examples of energy. So, and that energy is going to be in the form of electric and magnetic waves. Now, the thing about energy kind of has a dual property. It kind of acts like particles, right? It moves like a particle, but it also has that wave function. It also moves like a wave, like a tidal wave, you know, okay? So a couple of things that we want to keep in mind about energy. Energy is always going to be transmitted at the speed of light. Doesn't matter the type of energy, it's always going to be transmitted at the speed of light. And of course, you know, these are under ideal circumstances, perfect circumstances, right? That nothing deflects it or interferes with it. In that case, energy is traveling at 3.088 times, I would say 3.00 times 10 to the 8th meters per second. Okay. Now, earlier, we were talking about the fact that it has a wave-like particle, right? Or wave-like pattern just a second ago, right? So in other words, it does this, right? So energy travels like that in an oscillating form, right? So this here is peak to peak. So if we go from peak to peak, that is called the wavelength. Now let's say we had a barrier. We're going to put a barrier here, okay? So the number of oscillations that happen within a time frame, that's called our frequency. Okay, nu equals frequency. Looks like a G. And this guy equals wavelength. Now the wavelength is a distance. It's the distance from peak to peak or trough to trough. Okay, so it's a actual distance. Okay. So if we multiply these guys together, how many oscillations that happen per second times that distance traveled, you know, then that's going to give me the speed, right? Which is the speed of light. And the speed of light is always a constant. Do you guys know what I mean by a constant?
Something that doesn't change.
Something that doesn't change. So it's always going to be the same, right? So the speed of light, c, is always going to be 3.00 times 10 to the 8th meters per second. So that means our frequency and our wavelength are going to have to change, right, when they're together. So as the frequency increases, the wavelength is going to decrease. So as this is that funny looking V that I draw, that's frequency. As that increases, the wavelength is going to decrease. Okay, so that's called indirectly proportional. We talked about that in chapter 3, right? You guys remember we were talking about density and all that stuff? Okay, and vice versa. As the wavelength increases, the frequency is going to decrease. Okay, so I'm going to show you that here in a second. But I wanted to talk about one other thing. We're talking about energy, right? So I'm going to give you another equation. E for energy equals H. H is Planck's constant. And nu, that V, although I can't make it my funny looking V on my board. Okay, so for H is Planck's constant. And nu, that V, equals frequency. Okay, so this allows us to look at the frequency, or we could even look at the wavelength and associate it to energy, right? So we know that Planck's constant is a constant because it says it in the name, Planck's constant. So it's always going to be the same. So regardless of the value, it's always going to be exactly the same. So that means that we're setting energy directly proportional to frequency. So as frequency goes up, what's going to happen to the energy?
Is it going up?
It's going to go up. That's right. That is right. So they're directly proportional. As one goes up, the other one goes up, right? Where in the case of wavelength and frequency, it goes down. So in theory, we can sit there and use this equation here to calculate our frequency, and then we can use the frequency to calculate the energy. Does that make sense?
Yes.
Yeah, good. Okay, so that brings us to next slide. I'm going to clear my screen. I'm going to write up everything else I need. Okay. So here, this is just basically showing us the electromagnetic spectrum. So this is just showing us from a certain frequency all the way to another frequency of all of the different types of waves that we have. Like, for instance, these guys are my X-rays, right? So from here to here. So that represents X-ray for X-rays. Okay, so if we look at the wavelength, these guys have very, very small wavelengths, but they have very high frequencies, right? So since the wavelengths, since they're very, very small in terms of wavelength, their frequency is higher, right? As we move in this direction, we have I'm sorry, these are not X-rays, these are gamma rays. Gamma rays. Have you heard of the Incredible Hulk?
Yes.
Okay, so do you guys know that his origin, it was gamma rays that made him the Incredible Hulk?
Yeah.
Right. Okay, so those are the rays that made the Hulk the Incredible Hulk. In reality, that wouldn't happen. Gamma rays would kill you because they actually are so small. The waves are so small that they're able to actually go through your skin and through your cells, and it just damages, it destroys your DNA, and it destroys it immensely because those wavelength, that energy, the wavelength of energy just goes in and just breaks up that DNA, and so it really just destroys us completely. That's what happens in reality. Okay, so X-rays again, you think about it, this is the size of a molecule, right? X-rays, the wavelength for an X-ray is in that range, right? So if you think about it, a single atom, right? Our DNA is made of tons and tons and tons and tons and tons of atoms, right? And then so it could do serious damage to us as well. So high exposure to X-rays will do exactly the same thing. It will actually destroy our DNA. And so that's why they have to limit the exposure that they give us. You know, have you guys noticed, like when you go into the doctor and you're getting checked out to see if you broke your arm or whatever, they stick your arm in there and they only stick your arm in there, right? And then they do it really quick. And then they're really hesitant about doing another one. And that's because X-rays cause damage to your DNA, right?
Is it the same as sonograms? Or is that just different?
Sonograms are a little different, right? But that's going to be at a different range, right? So sonograms is based upon sound, right? Sound waves. Sound waves comes down on this other end, okay? And so those waves are bigger, so they don't do as much damage. So that's why they use it to see if, you know, if you're pregnant and where the baby's at, how the baby's doing, right?
Mm-hmm.
Because those waves are so big that they're not able to go through your skin and go through your, so they're just relying totally on the sound. So that's a little different. Okay, does that make sense?
Yeah.
Okay, good question though. And that's like one of the questions I like to put on certain exams. Is why do you use sonic waves rather than X-rays to determine whether or not you're pregnant? Okay, or a sonogram instead of an X-ray. Let's see. So X-rays fall in this range, and then we have UV light. UV light is the light that, you know, that light that comes off the sun and everything like that we always have to block, right? Or you guys have the UV light bulb and stuff, that purple light, you know, makes everything glow. You can see DNA with it, all that stuff, right? Okay, so UV light is a form of energy, and it's also in waves, right? Visible light, that white light. So this here represents the full spectrum of white light. So if we break up white light, you guys in your kit, you got a little slide, which we'll be using this week. One of those days. Okay, so for this week, you're going to need your black paper for your lab this week. You're going to need your diffraction slide. Okay, so if you guys have your diffraction slide at a point, hold it up to the light. Now, don't look directly at the light, look towards the side, because then you'll see a nice little spectrum. Okay. And so you'll get a beautiful spectrum of light that'll show you, like, it'll be from the blue all the way to the red, and it'll go in a nice little gradient. Okay. So on Friday, you're going to need those two things because we'll be building a spectrometer. Okay, so you're going to need these two things, and you're going to need your glow sticks. Okay, or one of your glow sticks at least. Okay. Okay, so moving back on. So this is the visible spectrum, right? So if we use this slide, we can actually separate all of the different colors of white light into that spectrum. So we can get this visible spectrum. I call it the spectrum. So this is called a continuous spectrum. As you guys can see, all of the colors kind of blend into each other. So that's the reason why it's considered continuous. I mean, human thought. It's considered continuous, okay, because they all bleed into each other. So how would we use this information, right? Let's say, for instance, we have a photon of, let's say, green light. Green light, look at it, it's somewhere between 500 and 550 nanometers. So that's going to be the wavelength that it has. So if it's 505 to 550, let's say 525. So the wavelength is 525 nanometers. Can I calculate the frequency of that green light? Yes, no, maybe. Not in a million years. And if so, how? So I want to calculate the frequency. What is the symbol for frequency again? We just talked about it. Anyone? Okay. Well, the symbol for frequency again is nu. So if I remember correctly, I have that equation where the speed of light equals lambda times nu. So I want to solve for nu. Kind of like the question in the problem. So I'll get C divided by lambda. Now, lambda is in nanometers. And C, if I remember correctly, is going to be equal to 3.00 times 10 to the 8th power. And that's going to be meters per second. So I'm going to plug this guy in. .00 times 10 to the 8th. Meters per second over 525 nanometers. But didn't I just say these guys are in meters per second and these are nanometers? So do those units match, meters and nanometers? Are they the same unit of measurement? So no, they're not. Right? So they're not the same unit. I mean, they're measuring length, but one is measuring a value at a much smaller range. So we have to convert our meters into nanometers. Okay, so I'm going to have to use my conversion. 1 meter equals 10 to the 9th nanometers. Okay, so then nanometers are going to cancel out. So let me simplify this. Okay, so if I do the math, I should have 3 sig figs times 10 to the 14. And that's going to be hertz, or just 1 over seconds. Okay. Questions? Concerns? Dash? Credit? This is going to be on the exam, not this exam, but your next exam. Okay? Fair? Good. Okay, so if we go through and we take a look at this, right? So it kind of give you an idea of that distance. You know, like I said, this here is an atom, so that's going to fall in our X-ray range. Our UV range is going to be about the size of a virus. A bacteria cell, that's going to be an infrared range, which is greater than visible light. Okay. Animal cells, this is the thickness of a CD, so that's going to be the wavelength for a microwave. The width of a CD, still about the wavelength of a microwave. Your radio waves, about the size of a dog. Right? So those waves are going to be pretty huge, the wavelength for those, okay? Okay, so let's move forward. So we've talked about the continuous spectrum. So there's also what we call the line spectrum. The line spectrum is basically, it's basically discrete lines where they've been separated. So that light, that visible light, or the spectrum has actually been separated into individual lines. So like, for instance, if we take an element, let's say hydrogen, and we put it in a tube and we excite it with a whole bunch of energy, it's going to give us a discrete line spectrum or a line spectrum. And that spectrum is going to be unique for hydrogen. So every element is going to be unique. It's going to give us a very unique spectrum associated with it. Okay. So when we talk about electrons, right? And we've talked about electrons already. You guys are already familiar with it. Electrons are able to be excited, so we can put energy into that electrons. So what happens is that we have what we call the ground state of the electrons. If we put energy into that electrons, we can excite that electron to a higher state. How many of you guys have kids? I know I heard a kid earlier today, so you guys can't act like you don't have any kids. Anyone? Daughters, nephews, nieces? No children? Okay. Well, there's some kid in your life. I'm going to ask you specifically. So Halloween is coming up, right? Is that true, Brittany? Okay, so Halloween, we always get candy. Kids get a whole bunch of candy. Now, what if your kid or the kid in your life eats all that big old bag of candy in one night? What's going to happen to that kid?
They'll become diabetic.
Guys, you go from extremes. I mean, you didn't get halfway there. They'll become diabetic.
We're jumping everything.
They will be jumping and they'll be excited. They'll be running around the room, right? All crazy. And then
They'll be like a gas atom bouncing off walls.
Exactly, bouncing off the walls. Exactly, right? They're gonna be crazy, right? Unmanageable, running off, throwing up everything, destroying everything, right? And then eventually what's gonna happen to them?
They're gonna crash.
They're gonna crash. Totally crash, right? So the electron is like your kids, right? Or like the kids in your life. If you feed them a whole bunch of candy, you give them a whole bunch of energy, they're going to get really excited and they're going to jump up really, really high and be crazy, right? And then eventually, all of that energy has to be released and they're going to crash, okay? Now, when that energy is released, they actually emit a photon. They emit light, right? And so we see it as light. And each electron has a unique signature about it that you have a very discrete emission of light. Does that make sense?
Yes.
Okay. So let's get into that a little bit.
So
Okay.
can we say that every color we see when the emission of light is like a different level of energy from a photon?
Yes, when you separate them, yes, you can say that. Yeah.
Okay.
Good analogy. See, you got it there. You see how it works. Okay, so light acts like a wave and it acts like a particle. It acts like both. It has that dual property. Okay, so here's that wave part of it. Okay, so we have that wavelength, as I said, was peak to peak or trough to trough. And so this here represents the wavelength from peak to peak. Okay, and as we can see, the wavelength of A is greater than wavelength of B. Wavelength of A, it has a lower frequency. We have 1, 2 waves before we hit the rocks. Where the wavelength with B, it has 1, 2, 3, 4 waves, right? So as the wavelength decreased, as lambda decreased, our frequency increased. Okay, so we had more peaks crashing the wave, right? So if we disperse white light using the diffraction slides, we get a nice, beautiful, continuous spectrum, right? If we disperse an element that's being excited by putting energy in, right? In the case hydrogen, we get very discrete line spectrum, okay? And as Cassandra was saying, each color are going to represent a different amount of energy, right? Because each of these colors represents a different wavelength. And since each of those colors represents a different wavelength, we can use the wavelength to calculate the frequency. Like we did earlier. And then we can use the frequency. Oops. I can fix my new. And we can use the frequency to calculate the energy. Okay, so if I have my wavelength, I can calculate my frequency. And with my frequency, I can use that to calculate my energy. Does that make sense?
Yeah.
So then
Is that what we're going to be doing? Is that what we're going to be doing for the lab? Okay.
Yeah, that is exactly what you guys are going to be doing for the lab. Yep. Okay. So, and it's going to be based upon the different wavelength that we get from the different colors. Okay. So this is, again, this is hydrogen being excited, and then this is the energy, the different energy released by different electrons that are being excited. So we know that hydrogen has one electron, and it works beautiful for hydrogen. Show you. So we'll notice that we have one that's a blue, one that's kind of, I don't know what that is, that's that teal or something like that, lime green, and red, right? So that one electron has the ability to be excited. Depending on how much energy you put into it, it can be excited just a little bit, or it can be excited a whole bunch. So if we think about this, the wavelength here is, it's going to be like 420, right? The wavelength over here, that's going to be like 650. So the wavelength is increasing, right? So we would expect the frequency to increase or decrease.
Decrease?
That's right. We would expect the energy, the frequency to decrease. So as the wavelength increases, frequency decreases. Okay, so we would expect the energy to be more or less for 400 or for 600. Because we know that energy and frequency, so as frequency decreases, energy is going to do what?
Decrease.
It's also going to decrease. So we'd expect that energy to be less for the 600 than for the 400, right? You guys are with me?
Yeah.
Okay. So this here is the discrete line spectrum for mercury. This is for neon. And you can see, although they have colors that are similar, but where they're located at and their wavelengths are different, right? And how many that there are different. Okay. So you can see they're going to have different patterns. So every element has a unique pattern associated with it because of the number of electrons it has and how much energy those electrons can take up. Okay. Does that make sense?
Mm-hmm.
So somewhere on your beautiful sheet of paper, you may want to, the sheet that you guys get to use for your exam, you may want to record these equations. Let me make my pretty one. And remind yourself, are they directly proportional or indirectly proportional? Although you can put numbers in and figure it out, but do it quicker, saves you a lot of time, right? Okay. So again, I guarantee you're going to have a test question, not on this exam, but the next exam that will have this on there. Okay. Ready to move forward? Okay, excellent. I love consensus. Okay, so there's this guy named Bohr. Now, and not like he's a bore, but his name was Bohr. Okay, so Bohr had basically said, okay, so we have these electrons, right? And we know these electrons are outside of that nucleus. And, I kind of think that these electrons are orbiting that nucleus, right? And they're kind of orbiting in terms of like energy levels, right? So we have that ground state energy level, which is that normal orbit that it goes through. As soon as we stick in energy, we pump it up with energy, it gets excited and it goes outside. Then it'll orbit outside at a higher energy level, right? And he's like, this is kind of like that concept of quantization, right? The fact that we could have those discrete lines set up, each one representing a different energy level, right? Rather than having a very continuous line set up, okay? So he's like, I kind of think of it like that. So we know that like white light, it was all nice and continuous, but those elements, the way those electrons are working, they're very discrete. So if we take a look at it, it's like this. This here represents that continuous white light, right? Where Bohr was postulating that it's really like each of these being steps, right? Steps of energy, okay? Can you guys see that?
Yes.
Okay, so continuous and steps, okay? So Bohr's atom, he basically designed his model based upon the hydrogen atom. He tested it out on the hydrogen atom. And guess what? It was almost perfect, right? His data was very consistent. It worked out great. So the electron, this represents the ground state, okay? This is the energy that would be associated with it. As soon as he put some energy into it, it popped it up. It could pop it up to that second energy level. It could pop it up to the third energy level, or it could pop it up to the fourth energy level. Now, the thing is that it was able to pop it up without having to go through each of the different energy levels. It just kind of skips over it. You just put enough energy and it just pops it all the way up, right? So that there is called a quantum leap. The fact that it didn't have to go through each different level to get to the next level. Does that make sense?
So far, yes.
Okay, good. Now, again, this worked beautifully for the hydrogen atom. Why do you think it worked beautifully for the hydrogen atom? I'll take a guess. How many electrons does hydrogen have?
It only has one.
It only has one electron, right? It only has one electron. It's really easy to do anything with one electron. How many of you guys have multiple kids? Anybody have more than one kid? Or
I only have one, and it's easy right now.
It's easy right now. So because you have that one, right?
Yeah.
So how many of you guys have multiple siblings?
I have two brothers.
You have two brothers? Okay.
Yeah.
So was it easy? Are you the youngest or are you the oldest?
I am the youngest.
You're the youngest?
Yeah.
Oh, so you got it. You had it hard in the very beginning, right? I was going to ask you, was it easier when there was just one, or was it, So with anything, right? If you have just one, it's real easy. Okay, watch them. They're going to do exactly what you think they're going to do, right? Okay, yeah, I got them under control, right? But if there's two, then you always have that random element that's going to happen, right? And then if there's three, then it gets really crazy. Then there's four. Oh my God, it's just out of control, right? So the more you have, the harder it's hard to control it. So if you think about it, this one, we're putting all the energy in that one element. I mean, in that one electron, right? Mm-hmm. And then if there's two electrons there, well, one may get a little bit more than the other one. And so it may jump out and do something crazy, and it may affect that other one, right? Because if you guys have siblings, more than one, doesn't that other sibling always pick on the other one? You always have one that's just like always picking up. You just touch him. That was me. I was that sibling. I would touch my sister. I'd drive her crazy. Stop touching me. And then she'd get mad, and then she'd be swinging at me, and she'd hit my other sister, right? And so then it would all end up in a big old fight, and my mom wanted to beat my butt because of it. Who started that? So it's the same concept, right? The more that you're going to have, the more complicated, right? Okay. When we had that one, it was real easy. Okay. So Bohr's atom only worked for the hydrogen. Okay. So that meant that there's a lot more to it than that. And so a lot of scientists have basically worked on quantum. Quantum is still, there's still a lot of haze on it, but we have a good idea on a lot of it now. And that's what you guys are going to be kind of learning. You guys are going to be learning about the electron configuration, right? The fact that we can sit there and keep track of each electron independently and kind of what's going to be happening with that electron and how they're going to affect each other in ways too, okay? So that brings us to the quantum leap. I just talked to you guys about that. And that's just that the fact that an electron can actually, in an atom, an electron in an atom can move from one energy state to another energy state without having to go through each of the individual energy states, right? And if you guys look on your periodic table, I want you guys to recognize this now so we don't get too far in. Let me go up to the periodic table. Of course, now I can't find it. Table, there you go. Okay, can you guys see my periodic table?
Yes.
Okay, so here we have these numbers 1, 2, 3, 4, 5, 6, 7. So these numbers represent, this is called your period, right? So these also represent the energy levels, right? So these guys are going to represent what we call N, when we start talking about the quantum number, or the principal quantum number. Okay, so we've talked about hydrogen. Hydrogen has one electron, right? So it has one electron, it has one proton, and 0 neutrons. Okay, so that one electron, as I said, could be excited. It can go up to all of those energy levels, right? And as you saw, Bohr kind of mapped that out. It even had all of the energy levels that it could go up to and calculation how much energy it was and all of that stuff, right? But if we looked at helium, helium had 2, and that's the next thing that he did. He actually looked at helium, and he thought he was going to get very similar results and everything like that, but he couldn't control where the energy was going. He couldn't control how those electrons are going to respond to each other. So the electrons are interacting with each other in a certain way, as well as interacting with the energy that's being put into it. So it made it much more complicated. And the more atoms that were added, the more electrons that were added, different atoms, right? Different electrons, it got even more complicated, okay? So that brings us to why it got complicated. I can get to my slides. Okay. So the reason why the electrons fall back down, right, or release that energy is because it's unstable. Them being excited is just like those kids that are on candy, right? They're just, ah! And then they all crash, right? So it falls back down to ground state. And then when it does that, it releases that photon of light. And each of those photons are going to be different colors, right? Because they're going to be different wavelengths. And they're going to represent different energy that's being released or emitted, okay? So let me show you. Here's my electron. This is when I hop it up on sugar, or energy in this case. It gets excited. And then my electron then eventually will drop back down to ground state. Now, when it drops back down, it emits that photon. That photon is going to be at a different wavelength. It's going to be at a different energy. So then it's going to have a different color. It's going to have a discrete color that's associated with it. Does that make sense?
Yes.
Okay, so as I said, Bohr basically, he helped us understand that there were the principal energy levels, those periods, okay? So that principal quantum number, that very first quantum number we use, those are called our energy levels, or they're called our periods. We associate them with periods. We have the top, our groups, right? So that brings us to quantum mechanics. We're not going to go too much into it because all I want you to get out of it is electron configuration. But I need you to get enough out of it that you can understand how to do this. Okay, so you're going to have to bear with me. I'm going to give you some definitions. I want you to kind of stay on top and kind of pay attention for a bit, and then we'll go through that whole process. Okay, so we talked about the principal energy levels. There's 4 quantum numbers, and these quantum numbers they're kind of like an address for the electron. So each electron in an atom has a different address, right? Hydrogen is really simple. It has 1 electron. It's going to have 4 numbers that are going to be associated with it. That's going to represent where and how that electron is behaving, okay? So if I have helium, helium has 2. So the first one has 1 address, and then the second one have a different address. We're not going to go into the quantum numbers themselves, right? What we're going to talk about is just the electron configuration to kind of get an idea of where those electrons are at generally and not specifically. Do you guys understand what I'm saying? So what you're going to need to know is, you're going to need to know the principal energy level, right? So those periods. You're going to need to know the sublevels. So the sublevels, those guys are going to be, we're going to call it S. There's going to be a P. There's going to be a D. And there's going to be an F. Now, orbits, right, are orbitals. So orbitals, the S has 1 orbital. The P has 3 orbitals. The D has 5 orbitals. And the F has 7 orbitals. Now, the way quantum works is it's kind of set up so that if the periodic table gets bigger, we get bigger in terms of what we use. So we have the S, the P, the D, the F, and then we have what we call, it would be the G, the H, the I, the J, right? So if we look at the trends of orbitals, S had 1, P had 3, D had 5, F had 7, then G must have
9.
9. And then H must have,
11.
and I would have,
13.
okay? So you see that trick, okay? Now, each orbital is able to hold 2 electrons, okay? Each orbital is able to hold 2 electrons. It's kind of like a love seat, right? Okay? So S can hold a total of how many electrons?
S cobalt 2.
2. P,
4.
nope, if it has 3 orbitals,
Oh,
3
6.
times 2, 6. 10, 14, 18, 22, 26, 15, that would be 30, okay? Okay, now, fortunately for us, we only have enough elements to go to the F, okay? We haven't got to the G yet, or the H, or the I. So those are all just theoretical, okay? But I like putting them on the test. See if anybody pays attention to anything that I say, so. Okay. So we have the S, the P, the D, and the F. So let's go to the periodic table. And so we're going to kind of stray from our lecture notes, and then we'll come back to the lecture notes towards the end and work our way through it. If I can get there. Struggling today. Feels like a Monday. Okay, so I'm gonna slide these. Okay, so can you guys see the periodic table? Thumbs up?
Yeah.
Okay. Okay, so let me break it down. So I already told you that these guys, these numbers here, they represent the principal quantum number or the energy levels. Okay. So this here is going to represent the S sub level. Okay. This here is going to represent the P sub level. This here is going to represent the D sub level. And this here is going to represent the F sub level. Okay, now these two here, these guys are really located right here. They're placeholders right here. If we take a look, I'm going to give you guys a different look to the periodic table. Give me 1 second while my mouse. Can you guys see that? Okay, where here is where the F really is. And if you look at these guys are actually in the D. Okay, you guys see that? So can you guys see my full screen? I don't know what you guys can see or not. Can you see everything? The full periodic table?
Yeah, I can see it.
Okay, so, and if we take a look, hydrogen is kind of like, helium is really going to be over here, right? Even though they just use it to line it up with noble gas, but for this, it'll be located right here in that second position, okay? Okay, so that's our S. How many electrons does the S orbital hold? The S subshell hold? My question.
2.
That's right. Okay, so that's 1, 2. Okay, how many electrons does the P subshell hold?
6.
1, 2, 3, 4, 5, 6. How many does the D subshell hold?
10.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many does the F subshell hold?
14.
14.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, do you guys see that?
Yeah.
Okay, good. Okay, so now let's show you how to use this, right, to do electron configuration. So let's assume that we have, we'll start with hydrogen since hydrogen is easy. Okay, so hydrogen, what we're going to do is we'll put in the element that we're talking about. Okay, we'll put in colon, and then, I'm ahead of myself. Then we go to that very first energy level, right? And hydrogen has 1 electron in that first energy level. So we write the energy level, the number 1. It's in the S sub level, and there's 1 electron. So that would be the electron configuration for hydrogen. Electron configuration for helium. Start off the same way. It's going to be 1s2. And we know that in the S subshell, it can only hold 2 electrons. So we can't have more than 2 there. Okay. So if we were doing, let's say, carbon. So this guy would be 1s2. So let's put carbon where carbon's at. I'm going to erase these guys. Okay, so 1s2 represents the electrons that would be occupied by the S sublevel. Then it would be second energy level. So we'd put 2s2. Then this guy's P, so then it would be 2 P, and that's 1, 2. Do you guys see that?
So the exponent is always how many electrons they have?
That's right. Yep. Yeah, so the number following the superscript number following the subshell would be the number of electrons that are in that subshell. So that has 2 electrons in the P subshell. Okay, so let's do chlorine. So this is an interactive process. You guys got to work with me here, so I can make sure that you guys get it. And if you guys get it, then the people that don't show should be able to get it by looking at the video, right? Okay, so okay, so if we go with chlorine, we're going to start at the very beginning. So that's 1, 2. So that's 1s2. Then we go 2s2.
2s2.
That's right. Then we go 5, 6. So that would be
2p6.
2p6. And then we go
3s2.
3s2. And then we go
3p5.
3p5. Okay, you guys see that? Okay. Okay, so you guys ready for me to throw a curveball at you to make it a little bit harder?
No.
No. Okay, well, we got it, Okay, so after we get to the P, right, we have the d orbital. The d orbital has what we call degeneracy. So that basically means instead of it being on the 4th energy level, right, it actually is going to start off at the 3D. So this guy is going to be the 3rd energy level. So it's going to be 3D where we're starting off. And then this guy is going to be 4D. And then this guy is going to be 5D. And this guy is going to be 6D. Okay, so it shifts it by 1. Okay. And then that's the same thing that happens here with the F. It shifts by 2. So if this is 6, this guy is actually going to be starting off at the 4F. This guy is going to be the 5F. And then if there's one that was following it, that would be the 6F. Okay. So how are you guys doing so far?
Why does it do that?
It does that because it's all based upon energy level, right? So since it's based upon energy level, they found that the 3D, is actually a little bit lower than the 4S. So all of these guys, the way that we put them in order is all based upon energy. So like the 1S is lower than the 2S. The 2S is lower than the 2P. The 3S is lower than the 3P. The 4S is actually lower than the 3D. And so that's why it has to shift. So it'll actually, when we're putting electrons in, it'll go to the 4S first because it's lower in energy. And the thing about electrons and the thing about atoms in general is that they want to try to find the lowest energy state possible. They try to keep their energy low. It's kind of like us, right? If you guys were, you guys are currently taking my class, right? If I told you all you had to do to pass this class was to come in and say, Dr. Henry, your hair looks great. You have beautiful eyes. And that's it. And you'd get an A. How many of you guys would come in every day and say, Dr. Henry, your eyes are great. You have beautiful, your hair is great. You have beautiful eyes. None of you guys would do that? Be honest, don't lie, because I'm telling you, if it were me and I was taking this class, I'd say, Dr. Henry, your eyes, your hair is beautiful. Your eyes are great, and call it a day.
Yeah.
I'd be there every day saying that to you, right?
For sure.
I wouldn't miss a day, right? But because you would do that because it's lower than energy, rather than having to do all the Chem 101 homework and study for the exam and study for this. We want to try to find the easiest way to get to our goals, right?
Yeah.
So that's the same thing with these atoms. They want to try and find the easiest way to get to their goals. They want to use the least amount of energy as possible, right? We want to use the least amount of energy possible. None of us want to sit there and work all day, all night, and everything like that, and not have any fun, right? We want to just kick back, and, relax and watch TV or game all day, right? We want to do those things, right? And so the atom is like us. It wants to try to keep the lowest energy possible, right? We want to keep the lowest energy possible. If we could say beautiful without working out, damn, we wouldn't do anything, right?
So after zinc, when it goes back into the P sublevel, does it go back to 4?
That's right. So if we were talking about, let's do germanium, right? We'll do that as an example so we can see it. So it'll actually go back into the 4 level, right? So let's go ahead and we'll do germanium, which is Ge dot dot. Okay, so let's start from the very beginning.
1s1.
Is it 1s1? How many? 1s?
Oh, sorry. 2.
1s2. That. Okay, and then
2s2.
2s2. So we'll do this. Okay, that's my 2s2. Fix that 2.
2p6.
Okay, 2p6.
3s2.
3s2.
3p6.
Okay.
4s2.
4s2.
3d. 10. and then 4p2.
Okay. Okay, that's it. Okay, so you can see how it can be very tedious writing all of these out, right? Yeah?
Yeah.
Okay, so I'm going to show you another method of writing them out. This is basically using a noble gas core. Now, the way that works is that you want to find the nearest noble gas that is before that element, right? So what would be the nearest noble gas that would be before germanium?
Argon?
Argon, okay? So we would write GE AR in brackets, okay? And then we'd go from argon and write our electron configuration. So it'll be 4s2, 3d10, and 4p2. Okay, now the noble gas core, it represents all of these electrons here, right? So if we had wrote argon, electron configuration for argon, it's going to be 1s2, 2s2, 2p6, 3s2, 3p6. Right? And so to make our lives easier and not have to write all of those out, we put them in what we call the core. That's not the only reason. That's part of the reason. Okay. The other part of the reason is that the electrons that are not in the core are the electrons that we can use for reacting, right? So these guys would be considered valence electrons. So these electrons can be used for bonding or trading, or help gathering, So it's kind of like, this is the money that's in the bank. This is the money that's in your wallet. Does that make sense?
Yeah.
Okay. So these are the ones that we're going to be able to use to sit there and do things with immediately, right? These are kind of like on reserve. We don't want to touch those. We want to keep those in our savings. We don't touch them, That's to buy that big house that we want, 20 years down the line. Okay. Okay. So we use this core to sit there and make our lives easier because it represents all of those electrons that are there. So we can just use that noble gas core to sit there and signify all of the electrons that would be before that. So let's take advantage of that and write, let's say, europium. Okay. Do you mind if I erase? I'll leave this one up, but I'll erase the other ones down here so that it gives us room to write. Then I'll get rid of all my X's here. Okay, so if we go europium, what would be the nearest noble gas?
Xeon? Xenon? I don't know how to pronounce it.
Okay, xenon, you're right. So we'll put EU colon bracket okay, And then, so we'll start here at this point. So then after that, it is
6s2.
6s2.
4f7.
4f7. Okay. How are you guys doing? Okay. Good. You want to try one more for the road? Well, not for the road yet, but
Sure.
okay. So let's see. Let's do a hard one. What about TL? Selenium. Okay, where's it located at? Give me the group and the period.
Group 13, period 6.
Okay, group 13, period 6. So this is our goal. Okay. Okay, so there's noble gas. Say nearest noble gas before it.
Xenon.
Xenon again. Okay. Okay. Then
6s2.
6s2. And then
4f14.
4f14. And then
5d10.
5d10. And then
6p1.
6p1. Okay. Simple.
Got it.
Good. Okay, so let's go ahead and move forward. So you guys, that's electron configuration. Not too hard.
Is there any videos that we can like look reference to if we really
Yes.
don't get it still?
Yes. If you go to Maribel, actually, if you go to the link itself, there'll be a link to videos of, I should say, my lecture notes. If you go to my lecture notes, underneath my lecture notes or before my lecture notes, there'll be a link. There'll be two different links. One is Melissa Maribel, and I think one is Tyler DeWitt. So if you click on that, there's a video that you can watch to do that.
Okay, thank you.
Okay. And then there's also my video from last semester as well. Okay. And you'll have a few questions on this as well too. So just be prepared. Okay, so I'm struggling here. There you go. Okay, so we've already talked about the principal energy level. We talked about the N and what the N represents. We've talked about the S, the P, the D, and the F sublevels. We've talked about the order in terms of energy. The S is lower in energy than the P is. And so the S is lower than energy than the P, and the P is lower than the D. So the 3S is lower than the 3P and lower than the 3D. We've talked about degeneracy already. So you guys can see here, here's the 3S, here's the 3P, here's the 3D in energy, right? But you see that the 4S is lower. So you fill up the 4S before you fill up the 3D, okay? Now, when you're taking out, it's different. when you're taking out, you always want to go with the number that is the highest, the principal energy level that is the highest. So we would take out from the 4 before we take out from the 3. Does that make sense? And you're going to ask me, why is that? Right? So even though that these guys are at different energy levels, the 3D is lower. I mean, the 3D is higher in energy level than the 4S, but it's the energy level actually that it's higher. But the location of it is the 4 is outside of 3. So let's say, okay, so here's the nucleus, right? And this represents those energy levels. Okay, so if I have electrons out here in the 4th energy level, 1, 2, 3, 4, this is N4, this is N3, this is N2, this is N1, right? If I have electrons in the 4th energy level, wouldn't it be easier to pull from those than to pull from the ones that are closer?
Yeah.
Yeah. So I use an analogy. It's very inappropriate, so don't be totally offended. But I use the analogy of the nucleus being like a mom, right? A mom who has one kid, right? Is going to keep that kid really close to her, right? A mom who has a whole bunch of kids, right, isn't going to have all their kids close to them. They're going to have their favorite one close to them, and then, based upon age, probably so far away from them. Now, in the case of if you're taking away from the mom directly, the one that's closest to the mom, what's going to happen in that situation? You're taking a kid away from a mom.
It's going to be more defensive because it's closer to her.
That's right. That mom's going to kick your butt, right? You're going to have to use a whole bunch of energy to sit there and take it, because you have to fight that mom from that kid. Where that kid that's all the way across town, right? You could just click up and go, right? So it's easier to sit there. The further away you are, it's easier to pull that electron. Where the closer you are to that nucleus, it's going to be a lot harder to do that. Kind of like that mom, you got to fight that mom for that kid. Does that make sense?
Yes.
Okay, very crude analogy. You'll never forget it, right? Okay. We've talked about the orbitals, how many that there are. We said that the S has 1, the P has 3, the D has 5, the F has 10, and each orbital is able to hold 2 electrons. So that means the S holds 2 electrons. And if you guys take a look, when we take a look, we have the S, the S, right? 1, 2, D, 1, 2, 3, 4, 5, 6, the D, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and the F. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. So all of these, the S, the P, the D, all of these represent orbitals. So the S orbital is just basically going to be a sphere. And all of this is done mathematically, right? And it kind of represents the space in a 3D structure. So this here represents what the S is going to look like. So the Bohr atom is basically based upon a single electron orbiting the nucleus. So here's the S. These are your 3 p orbitals, right? So you have PZ, PY, sorry, PX, py, pz, right? And each one represents, the z represents the axes that it would be on. These are the d orbitals. This is your dz2. This is your dxy, dx squared minus y squared. This is your xy. This is your dyz, and this is your dyx. So these would be all 5 of the u orbitals associated with the d. And you guys don't need to know this. I'm just showing you, but you guys get an idea that the s is a sphere. The p is, the orbitals are like dumbbells. The d is just kind of a hot mess. It's like 2 sets of dumbbells together, but we have one case where it's a total hot mess. And the f is even much more complicated. Okay, so we don't typically show it. Okay, so the 1s is going to be closer to the nucleus than the 2s. The 2s is going to be on the outside. Have you guys ever seen those Russian dolls?
The ones where you open and there's a smaller one inside.
That's right. Yeah. So the shells or the subshells are like those dolls. So 1s would fit inside of the 2s. The 2s would fit inside of the 3s. The 3s would fit inside of the 4s. And inside you have each of, the 1s, the 2s, the 3s, and the 4s. And so it's just like another layer added on. So if we think about it, doesn't that doll get bigger the more layers we have?
Yes.
Okay, so we would expect the atom to get bigger the more layers it has. So knowing that, we have 1, 2, 3, 4, 5, 6, 7. Francium is going to be our biggest atom compared to hydrogen, which is going to be, based upon these guys, would be the smallest. Okay, because of those shells, right? We're adding more and more shells. Francium is going to have more shells than the hydrogen does. Does that make sense? So as we go down.
Yeah, but it wouldn't be the last one on the far right. Organesium. That wouldn't be like the biggest one.
We'll get to that. I promise you.
Okay.
Yeah, it gets a little more complicated, but we'll get to that.
Okay.
Yeah. So this guy would be the biggest. Like if we were comparing these guys, let's say we're just comparing these guys right now, the one in this group. The one, number 7, would be the biggest. And then francium is actually the biggest of all of them. And I'll explain that to you here in a second, I promise. Maybe give you a little more information. Okay. Oops. Let me go back. Okay. So we have this, it's called the Pauli exclusion principle. Okay, Pauli exclusion principle basically says that you can only have 2 electrons at max, 2 electrons in a orbit, right? You could either have, it could be unoccupied, meaning there's no electrons. It could have 1 electron, or it could have 2 electrons. Okay, that's it. Okay, so the most that you could have is 2 electrons, or you could have 1 electron, or you could have no electrons in that orbital. Okay, so that's the Pauli exclusion principle. Okay, we've talked about electron configuration. I showed you guys how to do electron configuration, that process of 1s, 2s, that is all considered electron configuration. Okay, this is showing you the degeneracy, right? So remember here, this is the 3D, this is the 4D, this is the 5D, this is the 6D, and then when we get to the F, it starts at the 4F. Okay. So this is just, it's basically just showing you the energy level associated with the electron orbiting. This is what we just went through, right? The electron configuration, right? And you'll notice we put the period there, the principal quantum number. We put the sub-level, and then we put the number of electrons that are in that sublevel. Okay, these are the electron configurations for the first few atoms. We talked about using the cores, right? So this is the neon core, so that would represent the neon core. This would represent the argon core. Although that's a typo, that should be argon core would be, that's a real bad typo actually. Sorry. Let me fix this real quick. So that should not be there. So this is the argon core. Okay, so this is an example of how we would write zinc using that argon core. Okay, so there are exceptions, okay? Now, with everything in chemistry, and I'm gonna say this all the time, you're always gonna run into exceptions, okay? I'm not gonna hold those exceptions, you accountable for those exceptions. If you can give me the electron configuration for those circumstances, then you're good to go. But there are gonna be some exceptions that are gonna happen, and that's also based upon energy. So there's certain elements that the energy level gets skewed for some reason. And so as a result of that, they'll pull an electron from the S subshell to put into the D subshell and to make it a little more stable, okay? Yeah, come on now. So what I'd like you guys to do is, can you guys write the complete electron configuration for chlorine, if you can write it the long way and the short way, okay? So with the noble gas core. So I'll let you guys do that for a second, and then we'll do it together. So we're doing chlorine, right? So where's chlorine located at? Can you guys see my periodic table?
(17.3).
17.3, okay? Okay, so we have Cl. So let's do it the long way. So we're going to start off where?
1s2.
1s2. Okay.
2s2.
2s2.
2p6.
2p6. Okay.
3s2.
3s2.
3p6.
3p6, are you sure?
Oh, I'm sorry. 1, 2, 3, 4, 5.
3p5. Okay. So the short way?
Neon. Three S2. 3p5.
Okay. Questions? Concerns? Cash? Kool-Aid? Okay. Good. Let's move forward. Okay, let's see. Why am I struggling here? There we go. Okay, so cobalt. So let's write cobalt the short way. Where is cobalt located?
Nine, 4.
Okay. So cobalt, CO. So what is the core? Here's noble gas before cobalt.
Argon.
Argon. Okay.
4s2.
4s2.
3d7.
3d7. 1, 2, 3, 4, 5, 6, 7. Okay. That's it. Not too hard.
No.
Okay. Okay, so when we talk about valence electrons, we're going to be focusing mainly on what we call the main group, because those transitional elements and the post-transitional elements, those guys, they march to their own drum, right? They're a little bit different. They're going to be a little more complicated. And so we're going to be focusing solely on the main group. You guys remember which ones are the part of the main group? Main groups. It's going to be this guy and these guys. Okay, so group 1, group 2, group 13, 14, 15, 16, 17, 18. So basically just the s and the p orbitals. We're going to be focusing primarily on that, okay, when we're talking about valence electrons. Now, when we talk about valence electrons, we're looking at, let me take a step back. Okay, so I think we talked about it earlier, where everybody wants to be like the noble gases. Did we talk about that? Okay, so let me remind you, everybody wants to be like the noble gases. Okay, the noble gases are cool, they're stable, right? So I'm going to ask you a question. Be honest, be totally honest now about it. Gabriella, I'm going to ask you, and then I'll ask Alberto. Okay, so if you could date a doctor who has everything established, that pays for everything, that pays his bills, take you on really great dinners and everything like that, or you could date a crackhead, which one are you going to date?
I'm going to date the doctor.
You're going to date the doctor. Okay, now Alberto, I'm going to ask you the same thing, exact same question. Sorry, Alberto. If you could date a doctor who's stable, has money, takes care of you, or you could date a crackhead, which one are you going to date? Alberto, are you there? You might have stepped away. Okay, so we established that Gabby has a head on her shoulder. She's going to date the one who's going to be stable, right? So the thing is that the elements are kind of like this as well, right? They want stability. Ultimately, their goal is to try to get stable. The thing is that not all of them are stable, right? We have helium. All of these guys are the noble gases. Nobility, when we think about nobility, we think about rich, stable, things like that. Noble gases are stable. Everybody else on the periodic table isn't. They want to try to get to be like a noble gas. And the way that you get to be like a noble gas, you want to be like them electronically, meaning that the number of electrons, you want to try to set up so your number of electrons are like that of a noble gas. And the way that you would do that is there's 3 ways. You can share electrons, you can take electrons, or you can give electrons. Are you guys with me?
Yes.
Okay. So the electrons that you're able to share take, or give, those are going to be your valence electrons. So those are going to be the ones that are extra that you can get rid of. Okay. So for instance, if we take a look at sodium, can we write the electron configuration for sodium? Short way.
Neon 3s1.
Okay, so the 3s1, that one electron, right? It's that one electron that sodium is away from being neon, right? Because otherwise it would have the same number of electrons as neon. That's why we put it in that core, right? So this guy would be the valence electron. So it's that electron that it could use to give away, to share, or to take, right? So it's going to basically use this one to give away because it just needs to get rid of one electron to be exactly like neon. Okay, so then it's going to go and become sodium plus. Sodium plus is just the same electron configuration as neon. Okay, then it's just like a noble gas. So that makes it stable. So sodium wants to be a plus to be stable, like neon. Okay, do you guys get that?
No, where does the plus come from?
Because we got rid of one electron.
So
Right,
now we
electron.
have an extra proton that makes it positive.
That's right.
Got it.
Yeah. Good question. Okay. So if we have chlorine, how far is chlorine from being a noble gas?
One away.
It's one away as well too, right? So in this case, chlorine, the electron configuration for chlorine is neon we had 3s2, 3p5. So if it gains one electron, then it's Cl minus, and it's neon for 3s2. Fix that. Three p6, or we could just call it argon, right? Core. So it would have the exact same number of electrons as argon does. Now, the fact that it has the exact same number of electrons, this is called isoelectronic. Okay, so we would say the chlorine ion is isoelectronic to argon, right? Meaning that it has the same number of electrons as argon. Okay, now these electrons here that are outside of that core are going to be my valence electrons. So for chlorine. So those are the electrons that I could use for bonding, for giving, or for taking. Okay, does that make sense?
Yes.
Okay, so remember, these guys that are inside of there in that core, we don't want to use those. Those are storage. They're for the bank. We're not going to mess with those. These are the only ones that we're going to use. Okay. Okay, so let me clear. So valence electrons are basically the electrons that we're going to basically be using for our reactions, or for bonding, or for taking or giving. And what we're going to do is to calculate our number of valence electrons, we just take the sum of those that are in the S and in the P. So if we take a look again to chlorine, see. So if we just looked at the S, this S, and this P, that would give me the number of valence electrons for chlorine, which is 1, 2, 3, 4, 5, 6, 7. Now, if we take a look at the noble gas, argon, 1, 2, 3, 4, 5, 6, 7, 8. Argon has 8 electrons around it. Everybody wants to reach what we call an octet. It wants to have 8 electrons around them. They want to be like a noble gas. Octet. Okay, helium is a special case. It only wants to have 2 electrons around it. So its octet is 2, right? So hydrogen wants to be like helium. So it only wants to have 2 around it. Does that make sense?
Yes.
And then lithium wants to be like helium. So it wants to get rid of 1 electron so it could be like helium. Okay. So it would also only have 2 around it. Okay. So, okay. Okay, so this is just showing you basically the Lewis structure. So Lewis structure is a nice way of depicting that, right? So let me clear. So we talked about sodium. Sodium has 1 valence electron. So what we do is for every valence electron, we will put a dot. Sodium has 1 valence electron. Magnesium has 2 valence electrons. Aluminum has 3 valence electrons. Silicon has 4 valence electrons, 4 dots around it. Phosphorus has 5 valence electrons. Sulfur has 6 valence electrons. And chlorine has 7 valence electrons. Okay, so again, the goal is to try to get it so that you have 8 around you, right? So in this case, sodium would like to lose that 1 electron, right? So then it would be like a noble gas. Okay. Okay, it says write the electron configuration for the highest occupied energy level for group 16. And what they want you to do is they want you to basically say N meaning your period, S, and they want you to figure out how many S's and how many P's are in group 16. So we're looking for the 0 parts, okay? So N could be energy levels. So if we go group 16, group 16, here's group 16. So how many S's and P's are in group 16? So how many electrons are in the S orbital for group 16? So for oxygen, how would we write that? What is the electron configuration for oxygen? In the simple way?
Helium, 2s2, 2p4.
Okay, so I have 2. So I'd write it N, meaning that it could be any energy level, S2, and P4. So that would always represent group 16. We write any of these guys, they're going to have, if we're just looking at the S and the P, they're going to have 2s2, 2p, right? 16. Let's go down to tellurium. There's going to be 2 in the S, and there's going to be 4 in the P. Do you see that? So we would just write it in this term right here. Okay. Okay, so let's move forward. Okay, so the next one it says, identify the group whose electron configuration for the highest occupied energy level is NS2 and P2. So if we go to our periodic table, which group is NS2 and P2? NS2 and P2. Which group would that be?
Groups 13 and 14.
So for
Or
remember
14.
14, that's right. So it'll be 14. That's right. If we said NS2 NP1, that'll be group 13, right? Okay. Okay, so we've already talked about the Lewis symbol. Again, this is called the electron dot symbol, or the Lewis dot structure. Okay, and so again, you want to put the number of valence electrons around it. So tellurium is in group 16. It has two valence electron in the S, and it has 4 valence electrons in the P. So then it has 6 valence electrons total, right? Okay, so we've talked about a little bit about size, right? So I told you, as we go down, it's going to get bigger, right? As we go across from left to right, it's going to get smaller. Okay, now the reason it gets smaller is because of the center of the atom. The center of the atom has all the protons in it. The more protons you have, it pulls those electrons closer to the atom, right? So because the electrons are constantly moving around it, it's going to be pulling in those electrons closer to the atom. Okay. So as we move from left to right, it's going to pull closer. Are you guys all there? Am I losing you all? Okay. So the size increases from top to bottom, and the size also increases from right to left. Okay. How are we doing on time? Okay, we're going to stop today here, since half you guys have already left, and I'll see the rest of you guys on Friday, and we'll pick this back up next week. Okay, so this should be enough to actually get you guys through the next homework assignment. I'll see you guys later. You guys have a good day.